Okay, so welcome to my talk on SlimNoC, a high performance, energy efficient network topology. These days we have massively parallel multi-cores and many cores that can have anything between a couple of hundred and a couple of thousand cores on the chip. And the big question is how to design these cores with a topology that gives us some interesting properties, like for example, high performance, low cost, and low power consumption. And the idea, high-level idea that we had was, let's take a look at some of the state-of-the-art rack-level topologies and see if we can use some of these ideas and port them to the on-chip setting. Right, so we have many of these possible targets, and we considered a couple of them, including FAT3, well-known diameter 4 topology, Dragonfly, diameter 3 topology, and Slimfly, diameter 2 topology, which has the lowest one out of all of these things. Right, so in this example, we focus on Slimfly in this example based on a special Hoffman-Singleton graph because it has lowest diameter and interesting properties that seem to be a good match for on-chip settings. For example, this guy over here gives us 50% fewer routers than the FAT3 with the same number of endpoints and 30% fewer cables than the same sized FAT3. Right, so this is our inspiration, and so let's briefly take a look at what Slimfly is about. Right, so the key idea in Slimfly is to lower diameter and thus the average path length, so that we have fewer routers and fewer links. And this is kind of equivalent to the following operation: we have some network with routers and with endpoints, and with some cables, of course. And the lower diameter operation is kind of equivalent to okay, in this example, we have also 3 hops between any two endpoints, right? So we need 3 hops to traverse the path from this guy here to this guy here. And this operation is kind of equivalent to removing some of the routers, at the same time increasing endpoint density and the remaining ones to have the same size network, and adding up for the missing links. And now this resulting design has lower diameter of exactly 2, so we need only 2 hops to get from one endpoint to the other. And now the key method to achieve this, at the same time having high performance and a couple of other properties, is to use the so-called Moore bound, which is the upper bound on the number of vertices in a graph with given diameter and radix. So this means that, let's take a look at this Moore bound in more detail. So we are given some kind of graph with diameter d and with a number of ports, namely radix k. And to get to the Moore bound, we take an arbitrary vertex from this graph, which adds 1 to the Moore bound expression. After that, this one vertex has k direct neighbors, which adds k to the Moore bound expression, and each one of these neighbors has up to k minus 1 other neighbors, which adds k times k minus 1 to the Moore bound expression, and we repeat the step iteratively the diameter number of times to arrive at the actual Moore bound expression. Right, and the idea in Slimfly is to maximize the design of the topology so that it approaches the Moore bound, because it kind of intuitively inflates the topology with as many vertices as possible, at the same time having this fixed performance and cost properties of diameter and of number of ports per router, which means we have maximum scalability for a given cost and for a given performance. And thus it kind of sounds like a very nice thing for the on-chip setting, but is it really the case? And so in the straightforward first approach, we take the Slimfly and we try to put it on chip and see what happens. Right, so the default Slimfly design is as follows. We have the whole graph can be seen as 2 subgraphs, subgraph on the left and subgraph on the right. And the subgraph on the left consists of groups of routers that have the same intra-wiring pattern. So these vertical groups of routers has the same pattern of wires, but these groups don't have any connections between them, right? So these groups have some pattern of cables, but no connections between them. And the same for the subgraph on the right, but the wiring pattern may be different from the pattern on the left. But again, we have these identical groups of routers. And now these groups of routers are very densely connected across this partition here. So in such a way that they form a fully connected bipartite graph. And this design gives diameter of 2. And we try this design for the on-chip setting. So here we can see the results of the first attempt. We have 2 plots in which we compare different networks in the on-chip setting. So we compare flattened butterfly, well-known on-chip design, with a couple of variants. We consider 2D torus, concentrated mesh, Slimfly on a chip, and also for comparison for more data, Dragonfly on a chip. We do it for 2 metrics, for area per node and for static power consumption per node. And we also consider area due to different parts of routers and to wires, and similar for for power. And you can see that this design gives pretty bad results. So Slimfly on a chip and Dragonfly on a chip are much worse than low radix topologies such as Torus, and are kind of comparable to, especially in power consumption, to Flattened Butterfly, which is kind of the well-known and the powerful on-chip topology. So the question is, why is it the case? So what are the problems with this simple design? Right. So like the first class of problems is related to the buffer sizes. Right. So so we have this near best radix size diameter trade-off, but the problem is that as the network is low diameter, we'll have many of the wires traversing the whole die. Right. So and this is and if we have small for the short wires, the buffer sizes of these wires between these two connected routers are going to be small enough and do not pose any problems with, for example, power consumption. But if you have a wire that traverses the full die, then the buffer sizes will be larger for the full utilization, and this will give us, for example, power consumption problems. Right, so like kind of this length of wires and the size of buffers is the first big problem here. And the second problem is the number of feasible designs that you can use from the Slimfly domain to the actual on-chip setting. So here in this huge complicated table, which we do not really have to pay too much attention to with all these numbers, so these are basically different Slimfly designs. One row is one Slimfly design. We have different parameters for them, for example, router count or concentration. And now the point is that we have many of these configurations, but how many of them have the properties that are important in the on-chip setting? For example, how many of them have the number of nodes or routers being a power of 2, which is kind of the desirable metrics in the on-chip setting. Or, for example, equally many cores on each die side for easier manufacturing, or equally many routers on each die side, or, for example, equally many router groups on each side of the die for, again, easier manufacturing. Well, it turns out that the default design has only one such configuration, which gives us 16 cores, which is not really that many. Right, so the big second problem is that we don't have enough designs, enough configurations in the Slimfly design that allows us for easier on-chip manufacturing. So how to solve these problems? Regarding the first class of problems, the buffer and power consumption problems, what we do here, we propose a couple of area models and new layouts for better restructuring of this replacement of these routers in such a way that we minimize the power consumption and the wire length properties of the topology. Right? So the model must be generic enough to allow for arbitrary layouts because we may have arbitrary permutations of the position of these routers on a two-dimensional grid. And here these different mappings the sets of arrows will enable different layouts. To be more specific, what we do here, we either minimize the average wire length, which is given by just the sum of distances divided by number of links, or we minimize directly the total buffer area delta, which basically is the sum over all the buffers attached to each router. And we do have more details for this and provide ILP formulations for these minimization problems for reproducibility and genericness, and you can check the paper for all the details because they are a bit involved mathematically. So these models gives us a couple of concrete layouts that minimize these two things, minimize the average wire length and buffer size, total buffer size. Like we start with the basic layout here, where we basically take these groups of routers that we saw on one of the previous slides, and we lay out them next to each other such that we have one subgraph here and one subgraph here. And they give us some numbers, but then the easy way to improve this layout for having smaller average wire length and smaller buffers is to rearrange these groups pairwise in such a way that we kind of mix these groups pairwise by their type, and thus minimize the length of the links between these groups. As we remember, there are only links between groups of different types. And then if it's easier manufacturing, we can now merge these groups pairwise so that they form a kind of higher level groups, and these higher level groups are now having the same pattern of intra-wiring cables. So we don't have this. So in this final layout that we have a given number of groups. Each of them is identical, and they all are connected to the same number of wires, which is now easier to think about, to reason about, and to manufacture than this layout here, where we have these two different types of groups of routers, which adds a bit more complexity. And so now the question is, okay, what the difference do these layouts make for length of wires? So we have a couple of analyses for this. On the x-axis we have number of cores. On the y-axis we have average wire length. And we compare different layouts. So we compare this group final layout that we just saw. We compare this subgroup layout that we saw in the middle with these mixed pairs of groups here. And we also, for additional comparison, we also consider this basic layout from the left, the starting one, and the random assignment of routers. And the insights, the high-level insights are that the subgroup layout, so the subgroup and group layouts are kind of comparable as we scale number of endpoints beyond some level, and they differ somehow beyond this border of this 1,000, around 300 endpoints. And this initial layout and the random layout are similarly worse. And the insight is that if we consider the design with 200 nodes, it's best to use the subgroup layout, while it's best to use the group layout for the design which has 1,296 nodes, because it reduces wiring complexity and also it's very similar in performance. I mean in this average wire length. So now let's move to the second part of the thing, to the second class of problem, which was this missing number of configurations. And so we remember this table. We have one row per one slim-fly configuration, and only one of them was feasible for easy on-chip manufacturing, or for facilitating on-chip manufacturing. And so now the idea here is to change a bit the design of slim-fly, because the default design was based on a structural called finite field, and the idea was to on the prime finite field. The idea here is to use the other variant which is based on non-prime finite fields. And if we now consider the other table that has the configurations of slim-fly, basically of the underlying graph built using non-prime finite fields, it turns out that they can find many more of these configurations that are just more friendly for the on-chip setting, right? So we have many more of them that satisfy any of these, satisfy some of these constraints here, and we can use these to have more possible configurations, right? The question is how to design these finite fields. Well, this is not that difficult, and like the recap on the finite field is as follows. So you have this finite field based on a prime-based construction for slim-fly and slim-noc, and this is basically a set of elements from 0 to q minus 1, where q is this initial parameter for the construction of each of these topologies with modular arithmetic, right? So we just select q to be some kind of prime, for example 5, and basing on this initial parameter, we have some number of routers given by a well-defined formula. You can check in the report, and the field is basically a set of these numbers from 0 to 4 with modular arithmetic. And now the non-prime field is a bit more involved, but it's not that complex. So, like, one possible way to construct is basically to have a set of some elements 0 up to x q minus 1, and we need to provide instruction tables that define the operations on the field. So now the problem is that we can't really use anymore these simple numbers, natural numbers with modular arithmetic. We need to define operations that are just more arbitrary than these operations here. And one way to do it is just to have an exhaustive search over all these designs to have this table. And another well-known construction is based on polynomials. So basically, instead of these elements, you just pick a polynomial, a set of polynomials, and your addition, multiplication, division, and subtraction operations are basically operations not on these elements like here, but on polynomials. And this is also a well-known mathematical construction, easily to check. But the key idea is that you just use these polynomials and this construction to generate all these other designs. And so now let's, and the final part of the design is to apply some additional microarchitectural optimizations to make the performance and power consumption even better. Right, so we have combined design with a so-called central buffer router design, and let's just simplify for better clarity of the talk. So these performance optimizations are again targeted at high performance, low cost, and low power consumption, and these are three classes of optimizations. Like the first class the first enhancement involves so-called elastic buffer links and elastic store design, which is basically a design that improves a bit the size of the buffers, at the same time providing deadlock freedom. The second enhancement is to use smart links, which is a design where long wires that traverse the full die use a very careful placement of repeaters for making these wires single cycle, right? So we have this die that we saw before, and on this die, these long wires may have difficulties of achieving a single cycle latency, and this design here, I mean, that we use as a black box optimization is basically targeted at having a single cycle wires up to some frequency of the global clock. And the third one, so we reduce this size, and this again reduces the size of the input buffers. And the final optimization is central buffers. So a central buffer basically meaning that instead of having these I/O buffers here, we have only single fleet I/O buffers and replace these larger I/O buffers with a single central buffer in each of these routers to have again more power, less power consumption, and less latency. So now let's summarize. We took the high-level idea of taking a look at state-of-the-art rack-level topologies and considering them in the on-chip design. We've shown that the straightforward approach using Slimfly is not very efficient, and then we provided solutions to two classes of problems, namely to the wire length and buffer size problem, and to the lack of configurations problem, and also provided a design based on a couple of optimizations for more performance and less power consumption. Now let's take a look at how this fares in practice. So in our evaluation, we considered a couple of metrics: latency, throughput, buffer area, buffer size, and some variants of power consumption for different workloads, considering different topologies, namely concentrated mesh, 2D torus, flattened butterfly, and a variant called partition butterfly, as well as very briefly hierarchical networks on chip. For a multitude of parameters, naming layouts, different layouts, concentration amounts, different router cycle times, technology node, buffer types, injection rates, microarchitecture enhancements, so checking if these things actually matter that much or not that much, wire types, network sizes, and types of routing. Briefly, because we focused on deterministic routing and also did a minor analysis on the non-minimum adaptive routing. So the results for the performance are as follows. On these three plots that correspond to three different traffic patterns, on the x-axis we have injection rate, and the uplink links. On the y-axis we have latency in cycles. We use cycle accurate in-house simulator, and we compare. So different data sets are different networks, right? So we have concentrated mesh, 2D torus, partition flattened butterfly, and flattened butterfly here, two variants of partition flattened butterfly, and SlimNoC. The size of the topologies is around 200. So we can see here the latency for Slimfly is the lowest. As a direct consequence, kind of summary of all these things that we've seen. For the area and power consumption, we use a different simulator called Descent Simulator that does the simulations for these two metrics. And here on these three plots dedicated to different metrics. So here we have area per node, here we have dynamic power consumption per node, and here we have static power consumption per node. X-axis are different topologies, and y-axis are the values of the metrics. We also have a bit more fine-grained analysis into, for example, in dynamic power consumption, what is the main ingredient or what are the ingredients of a given number. And you can see that SlimNoC here is better than hierarchics on-chip topologies such as, for example, flattened butterfly. And it's depending on the metrics, it's either kind of comparable or a bit worse than low diameter topologies such as 2D torus and concentrated mesh, which is kind of expected because these topologies here they are inherently low power consumption, right? So like this concentrated mesh, it's not much power, but the performance is much worse as we've seen on the previous plot. So now the next plot will show a kind of combined performance throughput per power metric that try to see what is the order of these topologies in these combined metrics, right? So here we have, for example, the results for the simulations that do parsec splash based trace simulations, again comparing different topologies for different variants of the benchmark. And here on the y plot we provide the normalized energy delay product, which kind of combines these two metrics, the throughput and the power. And you can see that in these combined metrics we are having the best result. Right, so we have similar advantages when moving from the size of 200 nodes to almost 103,000 nodes. And yeah, we have also many more results that are available in the report. So the final takeaway message is what is SlimNoC? Right, so SlimNoC is a low latency topology. We have lowest latency out of our designs as a direct consequence of the low diameter and additional optimizations. It's an area and power efficient topology because it provides significant improvements over higher order topologies. It's a topology that provides the sweet spot in power performance, as we've seen on the slide before, and it's a scalable one because we preserve these advantages while moving from reasonable high amount of nodes to the high number of more than 1,000 nodes. Thank you for your attention, and I'll now take your questions.